Yeah, good morning. Welcome to Applied Mathematical Finance. We are still in our section on interest rate models, the discrete forward rate term structure model. So our big model that models a discretized interest rate curve, so not a continuum, but a discretized interest rate curve. We saw in the last session that it's maybe an advantage to consider this version of the model where we write the instantaneous covariance structure of the individual forward rates. So here is our forward rate L. So we have forward rates Li. Of course, in the background, there is our tenor discretization, the time discretization of the interest rate periods that gives us here the forward rate Li. And we saw in the last session that it was an advantage to write the model using these factor loadings which stand in front of independent Brownian motions. So here's the Brownian increment. So Ui is an independent Brownian motion, so independent implies that the instantaneous correlation is zero. Yeah, in this representation, we could very efficiently calculate the drift. So here our mu is calculated very efficiently. It's order n. Of course, I have to calculate the drift for every forward rate times m. So there is inside the drift is another loop, but now this on the order m. And as we will see later, it's often sufficient to have a fairly low number of factors m, say for example, like something like 5, a 5-factor model is already a very good, a very accurate model. So with respect to model parameters, we have the initial value, which will be given by our forward rate curve at that specific time. The factor loadings, which if you go to the other representation, so the other presentation was that one. So the factor loadings consist of a volatility coefficient and the correlation. In this representation, the correlation of the instantaneous Brownian driver if every forward rate has just a single Brownian driver. So the instantaneous correlation of the forward rates. So the lambda I is actually sigma I Fik, where the Fik's are coming from the Cholesky decomposition of the correlation matrix. Yeah, so that was the model that was maybe a good candidate to be implemented. So I like to start discussing the implementation, and you see implementation is here, the session that is coming here after today's session. So first, I would like to review discretization and Monte Carlo simulation. Okay, you think discretization, we already did discretization. But here, discretization refers to the discretization of the simulation time. So this means I observe my forward rate I just on a time discretization Tj. So this limits a little bit when we observe fixings of the forward rates. Note that due to our numeraire, the tenor discretization, so the index I, limits a little bit when we can perform payments because we know the numeraire only at these points. Yeah? At least if we do not specify here this short period bond. So discretization now refers to the time discretization of the simulation time of the stochastic process. So it's the second time discretization that comes into play. Usually we choose it finer because we also get time discretization error there. And Monte Carlo simulation then refers to sampling the random variable. Yeah, which random variable? Okay, I mean, of course, the random variable Li of Tj. Yeah, so L is an interest rate curve. Li's for the different i's is a vector of stochastic processes. Li of Tj, the stochastic process evaluated at a certain time, is a random variable. And now the next step is that I have to sample the random variables, so there will be different events, omega k, at which we sample the random variable Li of Tj. So I have an Li of Tj and omega k. So I like to first review these things. We have some building blocks, yeah, the Euler scheme, generating normal distributed random variables, yeah, because this random variable Li of Tj will be generated by our Brownian increment. So there will be here the delta W inside. I give you the example how we do that for the classical log normal model. So one version of our model, and how we then calculate the numeraire. So this is a little bit a recap. I use building blocks we already developed in the numerical methods lecture. But if you did not follow this lecture, it's not a problem, because this review is maybe enough, and you can just use this as a building block, some method that generates for you a normal distributed random variable, for example, or a time discrete approximation of a time continuous stochastic process. Yeah, given that the model is an E2 process, we can apply the numerical methods to create Monte Carlo approximation of time discretizations of the forward rates. So first, the time discretization of the stochastic process, so discretizing the simulation time, the Euler scheme. So now I make a small change in my notation. So I assume that my Brownian increments are independent. Previously, I used the letter U, UK, for the independent increments. Okay, but that was just to make the difference between my correlated Brownian increments and the independent ones, and write this in the alternative form. So now, since we stick to this alternative form, I will just relabel my independent Brownian increments W. Yeah, so delta WK is now the vector of independent Brownian increments. So my model is DLI is mu I dt plus lambda I dw. And note that here I dropped the sum. So previously I had here the sum k from 1 to m lambda ik duk. So now this is here in vector notation. So this is a scalar product. Okay, so it looks a little bit shorter. Yeah, lambda I is now the vector of these vector loadings, and dw is the vector of these Brownian increments. My Brownian increments are independent Brownian increments. So that means I have that dwk dwl is 0 for k not equal L. Maybe you already know the Euler scheme. So the Euler scheme of a stochastic process it's just doing the integral over dx from one time discretization point to the next time discretization point. So x of ti plus 1 minus x of ti, and if you move that to the other side, x of ti plus 1 is equal to x of ti, plus integrating from ti to ti plus 1, the change, dx of t. And now this integral, so you write the integral here on both sides, this integral is approximated by just freezing, so fixing the coefficients at the beginning of the time period such that they become constant. So it is a plus mu of ti, delta ti, the time step size, plus sigma delta w of ti. Okay, so maybe I should use j here. So because we have li, we have already a vector of random variables that are usually indexed with an I. So let's use j for this time discretization index. Then you could say, okay, let's just implement an Euler scheme of such a process. So we just freeze the coefficients here at time tj and we are done. But if you recall what we did, for example, for the Black-Scholes model, then it's sometimes an advantage not to do the Euler scheme for your stochastic process L, but use the Euler scheme for a different coordinate. For example, for the logarithm of L. If this stochastic process is a log normal process, means that you have an Li standing here and standing here. Maybe here, standing here and standing here. Yeah. So you have an Li in front of both parts. Then you can use Ito's lemma to remove that Li and move to the logarithm of Li. Yeah, and then in that case where, for example, lambda is a constant or piecewise constant, you will get a very accurate time discretization, because in that case, there is no discretization error here in the discretization of the diffusion, in the approximation of the integral of the diffusion part. So making the coefficients as constant as possible reduces this time discretization error. So, and sometimes you can make these coefficients more constant, or even you can make them constant if you move to another coordinate. So the Black-Scholes model is a good example. And this is now the motivation that I like to generalize my Euler scheme. So consider the classical Black-Scholes model, where my stock is a log normal process. So I have ds is rs dt plus sigma s dw. We observe there is an s here in front. So you know that in classical calculus, if you don't have stochastic processes, the derivative of s divided by s is actually the derivative of the logarithm. Here, if we consider the derivative of the logarithm, so I introduce y is log of s, then Ito's lemma will give us the dy. So you see, if you differentiate the y, it is logarithm 1 divided by s times ds. So it really effectively removes these s here. But I have a second order term, the second derivative. So second derivative, 1 divided by s is minus 1 divided by s squared, and then I get a ds. So there are two s inside, and I get a sigma dt, and because the second order term has a 1/2 in front, it's 1/2, I get a minus 1/2 sigma squared dt here from ethos lemma. So ethos lemma gives me the stochastic process of y, and from the second order term, we get this minus 1/2 sigma squared here. So I have dy is r minus 1/2 sigma squared dt plus sigma dw. So the nice part is if you now perform the Euler discretization, say, for example, of this part, integrating here, sigma is a constant, so it's just a sigma times delta w times the normal distributed random variable. For the special case of the Black-Scholes model, the nice thing is that this part here is also a constant. So we even have no time discretization error by integrating this part using the Euler step. So actually the Euler scheme is the exact solution. So once you have done the Euler approximation for the y, so our Euler approximation for the y is now that y at the new time is y at the previous time plus, okay, so now it is r minus 1/2 sigma squared delta t plus sigma delta w. Then you just apply the inverse transformation. So you go back and say s is the exponential of y, apply exponential on both sides. So you have s at the new time point is the exponential of y of tj plus r minus 1/2 sigma squared delta t plus sigma dw, which gives you then the log Euler scheme for s. So we have then the Euler scheme s of tj plus 1 is, okay, the exponential of the logarithm. I can move that in front. It is s of tj multiplied, because this exponential of a sum is the product of the two exponentials, r minus 1/2, exponential of r minus 1/2 sigma squared delta tj plus sigma delta wj. Okay, so these guys are the increments associated with this time step. And the Euler scheme below, the log Euler scheme, is much more accurate compared to the Euler discretization of the original stochastic process. In this case, it's even the exact solution. So I like to generalize my Euler scheme by allowing that there is some kind of state space transformation. So I introduce a function f and f inverse that transforms the original variable to the variable that I would like to discretize, and then the back transformation that transforms the discretization back to the original value. So I have a generalized Euler scheme for E2 stochastic processes. Since I have a vector valued stochastic process in my interest rate model, so the vector of the Li, the forward rates, I consider this here, of course, in vector notation. So x is the variable which we are interested in. So these axis here would correspond to our forward rates. So x would here be the vector of our forward rates. So this is the vector L0 to n minus 1. Okay, we previously used n for the number of periods, but now, since we also have this time discretization for the simulation time, okay, I have to be a little bit more precise with my indices so that they are not so confusing. So let's use maybe the letter D for the number of discretizations on the interest rate curve. So D is the number of periods we have on our tenor discretization. So this means I consider a d-dimensional stochastic process. But instead of discretizing x, I will discretize y, where x is some function f of y. So there is my state space transform here. This is my f, and this is transforming a background coordinate y, where we know the stochastic process for y. So y is now given as a d-dimensional m factorial E2 process. So this y corresponds to that we know the Black-Scholes model in log coordinates. And I know that my interest rate curve, my model primitives, my forward rates are a function of these random variables at certain times. Now I have the task to discretize the stochastic process y by an Euler scheme. The m factorial here on top refers to the fact that my Brownian increment is also considered to be a vector. This is a vector of m different m independent Brownian drivers. So my W is also a vector. So it's a W1, 2, and there we used the index m for the number of vectors. And m could be smaller. My discretization of the process y is the Euler scheme. So now we use the Euler scheme on y. So since I already have given y with my model parameters, so my model parameters are now the lambda coefficient for the y. So the lambda coefficient for the y does not agree or does not need to agree with the lambda coefficient for the x. So you see that here. So here the coefficient in the S state space is sigma times S. Here the coefficient is just the sigma. And also the drift may change. Yeah, so here it's an R times S. Here it's an R minus 1/2 sigma squared. So my model specifies the coefficients for the underlying process y. So we specified drift and the diffusion coefficient, the factor loadings for the process y. So maybe we have to do an additional step. Yeah, if you move to log coordinates and recalculate how does the drift look like under this coordinate transformation. But we will see, okay, this is just a similar adjustment like that. So I use these coefficients and the initial value to build up my Euler scheme. So the Euler scheme starts, of course, in the same initial value. The initial value of y is the inverse transformation applied to the initial value of x. And then I use the coefficients, the drift, and the factor loadings to generate, using my Brownian increments, the time discrete approximations of y. So now I use here the tilde, because it's no guarantee that my time discretized stochastic process agrees with the true solution. So when we have our time discrete approximation, so now I have my y tilde at tj, then I use my transformation, my state space transform, df, to obtain the time discrete stochastic process x tilde of tj. So I like to use this little bit generalized Euler scheme also because when we discussed here the model, that was our general setup. We had a collection of popular versions. And you see, there is here, for example, the log normal model. And now recall how the drift looks for our model. Well, we derived the drift for this version here. And in our derivation of the drift, we found that if we move to the measure q, then the drift was some, say, plus or minus, depending on terminal measure, spot measure, of a sum, well, running over some indices, depending on terminal measure or spot measure. And then it was that the drift mu I was a sigma I, sigma j, rho ij. So you see that in the drift there appears the sigma I. This is the sigma I in this general notation. So if we move to our log normal model, that one, this here is the sigma I of this general version. So I immediately know that the drift of the log normal guy, if we move to the equivalent martingale measure, is an Li sigma I Lj sigma j. So now this is this sigma here. So maybe I use the superscript here to indicate that it's the log normal one, Roj. So you see that both guys have an Li in front. Yeah. So sometimes you also see the log normal drift, just written as Li times mu I, say superscript L, where mu I superscript L is just this sum without this L part. So you see the special case of the log normal model has an Li here. So it makes sense to move to log coordinates for this special version. For our normal model, okay, there is a deterministic function here, could be also a constant, There will be no Li here, so we couldn't even move to log coordinates. Of course, because also the model allows for negative interest rates. There, we would not make this transformation. For our displaced model, you can now show that it's actually exactly the same argument that I have here in the diffusion part in the factor loading. I have an Li plus d in front. That means there will be, if you move to the equivalent martingale measure, there will also be an Li plus di in front. So then it will be sum of something. So you can also move to the log coordinates, because on the left-hand side you can write dli plus di. Yeah? So the differential of li plus di. So you can also move to log coordinates here. So the transformation depends a little bit on these special versions. So we may consider different state space transforms depending on which model we use. If we go to the special log normal version, you will observe that there will also be an Li here inside. So in that case, we can use the transformation exponential of x. So inverse is the logarithm. So we go to log coordinates, perform the discretization of log Li, retransform with the exponential. And funny, also for the displaced log normal model, there is such a nice transformation that will get rid of this coefficient and hopefully improves the discretization scheme. So that was on the time discretization of the simulation time, the discretization of the little t. Our next ingredient is that when we have discretized the model, we have to sample this random variable here, because this is somehow generating the whole stochastic process. So you see the initial value here is maybe just given. Yeah? It is the transformed initial value of x, and our initial value of x, if x is the vector of forward rates, is just maybe picked off a forward rate curve, which we have calculated. So then this here is just a functional rule that tells me how do I calculate the new random variable, given that I have the previous random variable and some functions of the previous random variable, okay, multiplied with this guy here. So this is a normal distributed random variable. And all these objects here are random variables. So this is an equation in random variables. And if you like to interpret it this way, if your initial value is just a constant, a deterministic value, the delta W is making the constant to a random variable in the next time step. And then it's just functions of this random variable plus an additional delta W. So my generation of risk, my generation of randomness comes from this delta W. So the next step is how we sample, how we generate samples of this delta W. So that's the Monte Carlo simulation. So to generate these, I would like to generate samples of this random variable. So now I have a vector. So it's a delta WK, k from 1 to m, my m factors, observed at a certain time, tj, j from 0 to n minus 1. And I would like to now sample this on different omegas, omega L, where L runs, say, from 0. Okay, I'm a programmer. I often start counting in 0, not always, to the number of sample paths, minus 1. So to generate a normal distributed random variable, so my Brownian increments are normal distributed random variable, there is the very nice inverse of the cumulative distribution function method. So you can sample uniform distributed random numbers, a uniform distributed random variable, and then if you apply the inverse of the cumulative distribution function. So this is here the phi inverse. In our case, it is the inverse, of course, of the normal distribution. Then you have that the delta W have normal distribution, or are samples of a normal distributed random variable. Okay, you know that Brownian increment delta W has mean 0, and it has variance being equal to the time step size. So if it is the delta W observed in Tj, it is the guy that moves from Tj to Tj plus 1. So Tj plus 1 minus Tj is the variance. So the square root of this is the standard deviation. So you can just sample a standard normal. In that case, phi is the distribution function of the standard normal, and apply a factor that is scaling to get the correct variance. Here the factor is square root of delta Tj. Yeah, that's an easy thing. So we can implement this. Okay, and the last step, the uniform random number generation. So my uj for the j's time step, ujk, k for the k's factor. So this is a family of uniform distributed random variables. So I sample the uniform distributed random variables by generating a uniform distributed sequence of random numbers. So you have random numbers generator, yeah, just implement it, and you can use these to generate the delta W's. By the way, I have here a uj k. Yeah? So you can now interpret this as a huge vector. Yeah? It is a vector of size m times n. So you have m different entries in your vector of the Brownian increments, but each increment at each time step is also independent. So I have here n time steps. It's n time steps and n plus 1 time discretization points. So you can think of this as being a huge vector of m times n elements. So think that you have 100 time steps or even more. You have 5 factors, so these are 500 entries in this vector. So this is a 500-dimensional uniform distributed random variable that we are sampling here. So I need to have a random number generator that guarantees still some decent independence of the entries in 500 dimensions. And if you think that Monte Carlo simulation is actually a form of calculating an integral, because all these guys are independent components here, and we are, when we take an expectation, we are integrate over all these components. This is a 500-dimensional integral. So you see that our model can become huge. And m is already the reduced number of factors. If you go back to the interpretation, to the version where each forward rate has its own Brownian driver, so this formulation where each forward rate has its own Brownian driver, and assume now that all these guys here are independent, or at least the rank of the correlation matrix has full rank. So I need n independent Brownian drivers. In my case, this n has become now a d, yeah, because I use n now for the simulation time step, and now d for the discretization time step of the interest rate periods. In that case, you would have that this guy would have d independent Brownian motions, as many as you have forward rates, and you would use n time steps for your time discretization. So for example, 100 forward rates, 50 years every half year. and 100 time steps. So this will be 10,000. This is a random variable in 10,000 dimensions. So this is a very high dimensional model here. So you also see from this aspect that it's maybe really important to reduce here the number of factors, reduce the number of Brownian drivers. Going from 100 to 5 is a big improvement. So the model is still 500 dimensional, but maybe that's also an improvement in terms of convergence. Let me discuss the steps again using the classical log normal model. So maybe we can go to this a bit quicker. So my argument was that for the log normal model, so that was here this special version. So for the log normal model, you see there is an Li in front here, and Li also in front of the drift. So it makes sense if we speak of Euler discretization to move to the log coordinate. So we move to the log coordinate. So my yi is now the logarithm of Li. And from Ito's lemma, you now have that you get a minus 1/2 sigma squared. Well, but this notation sigma squared was when there was just the scalar coefficient sigma here. So how does this look if the dw is a vector? Well, now this is just the scalar product lambda I times lambda I. So lambda I transposed times lambda I. So what's hidden here inside, in this norm, is actually dw times lambda I transposed times dw times lambda I, which is lambda I transposed dw transposed dw times lambda I, which is, and okay, this here is now the identity dt. So which gives me then a norm lambda I squared dt. Okay, so this relies on the fact that my cross terms in the dw here are canceling, because now I assume these are the factors of the independent Brownian increments. So my Ito's lemma will give me here the minus 1/2 lambda I norm squared. So the variance of the log Li, instantaneous variance. So now I apply the corresponding Euler scheme on logarithm of I. So we discretize logarithm of I. So the next value of logarithm Li at tj plus 1 is the previous value, plus the drift frozen at the starting time tj times delta tj plus the factor loading lambda I of tj frozen at the starting time tj multiplied with my Brownian increment. So the Brownian increment will later be then sampled with the Monte Carlo method. Going back to the exponential, so applying now my state space back transformation, which is my exponential, gives me my Euler scheme discretization of Li. So my Li tilde, because it is an approximation of tj plus 1. Note, for example, if you have the nice situation that the lambda is a constant, so with respect to the tj, it does not depend on time, then this part here of my discretization is exact. It's just the integral of lambda times dw. It's exact. This part here is also exact, but my mu was a complicated function of L. And yeah, there is the in the log normal case, there is still the Lj inside there. Yeah, so the log normal drift, yeah, if you remove the Li, that was this part here. It still has the Lj inside. So maybe I cannot use J now because J is my index for the time discretization. So you have a plus or a minus, you have some sum, and this sum is now running over all other forward rates, okay, so over some L, and now there is the sigma I Lj sigma j Roj, yeah, so there is still an L inside, so I do not have a constant drift. Yeah, and also note, I forgot here, also on the previous slide, this factor, there is the delta L divided by 1 plus, and there's even another L. So sorry, this is not a J, this is an L. Yeah, as I told you. O sigma L Y. Yeah, so there is an even another L inside. Yeah? So maybe I note here that this is an L. So this drift is not constant. Yeah, it's a complicated nonlinear function, and we will get a time discretization error from approximating this guy by using here the drift at a fixed time point. But apart from that, moving to the log coordinates is a good idea because it will make these parts here more accurate. If the lambda I of t is a known deterministic function, but maybe it is not a constant, sometimes it is possible to improve the accuracy because you can calculate, say, somehow like the effective increment, the Brownian increment, by introducing some lambda I bar, which is the integral of lambda I squared. So lambda I k bar is the integral of lambda I k squared over this time discretization step divided by the time discretization step, taking the square root. Yeah? So lambda I k bar squared is like the average variance accumulated over that time. And if you use this, yeah, then this here becomes an exact discretization, at least if we have no error coming from the drift. So assume I am under the measure that makes Li a martingale. So this measure is the Q PTI plus 1. Then I know that the drift is 0. Then I know that this problem here does not occur. So there is no discretization error coming from the drift. Then if I like to improve the time discretization error coming from the lambda, in the case where lambda is not already a constant, I can calculate the effective accumulated variance, which is my lambda I bar squared, and use that instead in my discretization scheme. So actually, this is the exact solution. So we may use the exact solution as our time discretization scheme. So to generate the time discretization. Yeah, so I have here an exact solution when I use here is the coefficient, something like the square root of the effective accumulated, the average accumulated variance. This is the exact solution for the case when the drift is 0. But of course, maybe it makes sense to also use this when the drift is non-zero, because then you get at least no discretization error from the correction factor that comes from the ethos lemma that we move to the log coordinates and from the diffusion part. So if the drift is not drift free, so of course I just have here the drift, but now I use my lambda I bar. Now I'm a bit sloppy with the notation. Yeah, so note here, I write now L in place of L tilde, but this should be an L tilde because it is still an approximation, because this drift here is approximated. But you see that creating an accurate time discretization of our original stochastic process is maybe a little bit involved. So we could try to replace our coefficient lambda with some averaged coefficient, averaged over that time step, to create a more accurate time discretization. And we could move to an alternative coordinate, to a coordinate such that our forward rate is the exponential of that coordinate, to also improve the time discretization, to reduce the time discretization error. And also, maybe you know this from numerical methods, there are integration methods that reduce, of course, the error of this drift approximation. The predictor corrector method is, for example, such a method. You may think that this is maybe here a special, very special property, that our diffusion model is such that I can calculate here this integral analytically. But what is very popular in practice and application is to just assume that my lambdas are piecewise constant. So here for this lambda bar, it could be just the assumption that the original lambda is a piecewise constant function, at least constant on this time discretization step here from tj to tj plus 1. This sounds like a brutal assumption. In that case, you have that the lambda I, which is the average of the lambda I bar, which is the average of the lambda I, is just equal to this, because your lambda I is piecewise constant on your time discretization step. But this assumption is not so brutal, because if you think that, for example, your time discretization of the stochastic process is actually a subset of your time discretization of the forward rates, how many financial products do you observe? You just observe maybe financial products on these times. So you do not have the information what the stochastic process is doing in between. So you do not have the information to calibrate a continuous time function in between. So for your model, it's maybe just okay to assume that the lambda I is a piecewise constant function, in which case you can just use this coefficient here and your model would not have a time discretization error because it is already piecewise constant. So that was discussing for the log normal model the time discretization, generation of sample parts. Okay, this is not special. So we just sample now our Brownian motion. So we have here a number of sample paths, and we generate our Brownian motion like we've discussed it. And in the end, we have a very high dimensional object. So I have my forward rate Li observed at a time point in my time discretization Tj as a random variable sampled on a path omega k. So we have the time index of the interest rate period is my I. The time index of the simulation time is my J. The index of the simulation path is here my K. Yeah, so sometimes I use also K for the factors, yeah, delta WK. So that's maybe a bit here ambiguous, yeah. So this is not the same I as this. Then I use omega L, but you see I'm slowly getting out of letters for the indexing. Last part, we need to calculate the numeraire. Well, our numeraire is a function of these random variables. So once we have generated samples of the forward rates at different times, I have a sample of my numeraire at different times. There is the slight thing that my numeraire can only be observed on the time discretization capital TI, because I need the forward rate to jump to the next numeraire, at least as long as we do not have the short period bond. If we do not define the short period bond, then I have my numeraire only at times little t equal ti. So I can now at these times, the times which correspond to the forward rate time discretization, my period time discretization, I can just calculate samples of the numeraire by just using here my samples of the forward rate. Yeah, it's just this function of a random variable where we use the forward rates L, here indexed with L, little l. Okay, for the terminal measure, I had a terminal condition. So my numeraire is the bond that is equal to 1 at the final time. So in capital T D, this numeraire is 1. And then I can discount with my forward rate. So it's 1 divided by 1 plus L times time period length, delta L, multiplied to that value to get to earlier values. Okay, so that's discounting. This gives me the numeraire at earlier times. For the spot measure, I have an initial condition. So we start with 1 unit of currency, and we always invest using the forward rate. We always invest over the period to the next time step. Yeah, note a slight difference. Here we observe the numeraire in TI, and it means I need to determine the value of this zero Cooper bond that is 1 at the end. So here I use all these guys in TI. So this means I have to recalculate this product again and again. Okay, so because these guys change. So this is the same TI as we have here. Yeah, so these two TIs here agree. But for the spot measure, we go forward, and it's just the previous numeraire multiplied with 1 plus LL TL. So the product can be calculated successively just by multiplying with additional factors. So that's also a difference in the implementation. There's maybe a little bit more efficient way to implement the spot measure numeraire. Yeah, that was a small tour on a higher level. And now I would like to create classes, interfaces classes. We like to structure our code. And I would like to follow a few principles. So the principles are designed for extension. So our framework should be designed for extensions. This is what we will do in this part here. I would allow maybe for very flexible specification of the lambdas. Because you see there is the normal model, the log normal model, the displaced model. There are many different versions. Actually, this is a model framework. So I would like to design everything for extension to allow that we can experiment with this. Then there is the single responsibility principle. So we would structure our program into small parts, and every part is responsible for a very focused task. For example, generate the normal distributed random samples that create the risk in our model. Yeah? So generate the Brownian motion, or calculate the drift, or perform the Euler scheme approximation. So I would like to decompose my program into these parts, designed for extension, and also the single responsibility principle profits a lot from specifying interfaces. So an interface is what can be done, but not how it is done. So what can be done means, okay, there is a method that provides me with the lambda, but how the lambda is calculated is not specified. And then there's a class that implements this interface that can be injected into this algorithm. So use this lambda to create the model, or use that lambda to create the model. So by writing our formulas in terms of interfaces, we have a level of abstraction that allows us to extend the program. And this injection means that there is a part of the program that has a single responsibility, for example, the responsibility for calculating this lambda coefficient. There is a third thing. Okay, these two first aspects a little bit go in the direction that we would make our program more modular, more finer. Cut everything into pieces and make the pieces small. There is a third aspect that goes in the other direction, and it is the requirement of coherence. So things that are connected or that belong together should be in the same component. And here there's a very nice example of this coherence. It is the calculation of the drift and the calculation of the numeraire. Because when you change the numeraire, the calculation of the drift will change. So the two have a very strong link. So spot measure numeraire gives the spot measure drift. Terminal measure numeraire gives the terminal measure drift. So you should not distribute this in two different places, because this will create the risk that your implementation could become inconsistent. Try to keep this together. We will discuss this then in the next session. Maybe I just conclude by looking at an implementation. Let's look at the implementation of this numeraire here. We looked at the implementation of the drift in the previous session. So we have maybe this coherence aspect here. So I already have an implementation, maybe not the best one. Yeah, there is still room for improvements, and maybe I can also discuss these improvements with you a bit. We have an implementation of our model here, and I will discuss this in details in the next session. And in this implementation, you see there is a function that provides the drift. And there's also a function that provides the numeraire. So maybe let's recall just the function that calculates the drift. It's this guy. So you see there is some lengthy documentation here. By the way, if this is hard to read, he will generate web pages from this documentation, and you can always move to this web page and read it there. So you go to the model, and then there's the documentation of the model, and there's also a documentation for all the functions. There's the function getDrift, and you see this Java doc documentation here is translated to this nice web page. Yeah? And you see you can even write LaTeX here inside. And this method implements the two drifts for spot and terminal measure using our model in the form where we use the lambda. Okay, this here is nicely written, a bit shorter as a scalar product. Okay, so our implementation of the drift was not so lengthy. It started there. Okay, and this is the last line where we return it, and we distinguished the spot measure and the terminal measure. So it was a sum. So you see the drift is here creating a sum. And for the spot measure, the sum was running forward over the indices. So we run here forward from the first forward rate. That is our MT. Yeah? And for the terminal measure, we run backward. Yeah? Okay, so now there should be the corresponding implementation of the numeraire. So for the implementation of the numeraire, you have to dig a little bit, because there are some aspects which we will discuss maybe in a later session. So the first thing is that this implementation here allows to adjust for a different discount curve. So you see there is something which I call the unadjusted numeraire, and then if there is a discount curve, there is an adjustment. Just put this aside, yeah, will be discussed later, but this comes a little bit from this fact, do we have a single curve world, or is there maybe a different discount curve compared to the forward rate curve? If you move into this numeraire unadjusted, there will be another step of pre-processing, or say it's actually a post-processing. It is this numeraire can perform some kind of interpolation. So we check, is the time that we provide here, is this time actually on our forward rate discretization grid? If this is not the case, then there is some stuff going on. If we are on this grid, we actually going to the numeraire unadjusted at the period index, and that's the code, yeah, that you may now find on this slide. So we are calculating this product. So for the terminal measure, our numeraire is here the product from my current forward rate to the end of my time discretization. So I take the forward rate, and then there is the discount here. The discount is divide by 1 plus L delta L. Yeah? So divide by this factor. So we are calculating here this product. We start initially with 1, going backward. Actually, the loop runs forward. We calculate the product that divides by all these. You see that when we call the forward rate here, it is the forward rate at the time index when we – observe this numeraire. So we run over all these forward rates. For the spot measure, actually, you do not see a loop here. No? This is because my numeraire is just take the previous numeraire and multiply that with an additional factor. So you see, my numeraire is take the previous numeraire, so just call this function again with the time index shifted by 1 to the previous time index. And then it is not discount, it is accrue. So this accrue is just, if you look at the documentation, take x and multiply with 1 plus L times period length. So this discount here is just take x and divide by 1 plus rate times period length. So all these functions here are actually functions on random variables. So there is an interface, what we can do with random variables, and all these functions operate on random variables. So we have an implementation of our numeraire in very general form. It just needs our model primitives here as an input, and we calculate the numeraire. Yes, that was it for today, and we will move to implementation in next session. Thanks.